Hello physics students, this is Dr. Berenzi and this is lesson 7.2.3, and in this lesson we're going to use the relationship between displacement and velocity to determine if energy is conserved in simple harmonic motion. In order for me to figure out what kinetic energy and potential energy are, I first have to know how to write displacement and velocity. So let's say that this is a displacement curve for an object that's in simple harmonic motion. Let's say it's a mass on a spring. So let's say that x of t, displacement is a function of time. Yeah, let's find a good place to put that. So this is x of t. And let's say that x of t is equal to 3 times cosine of 4 pi t. So if this is my displacement graph, what is my velocity graph going to look like? Well, I might get some clues from when I used to have displacement versus time graphs for constant linear motion. And what I found is that when you plot displacement versus time and something's going at a constant velocity, then the slope of the displacement versus time graph will give you velocity. So maybe I can use that on this graph here. Maybe I can figure out what the velocity around this region is, and then by finding the slope of the tangent line, and then do the same thing at different points along the curve, to give me an idea of what the velocity might be. So let's do that. So this is the same displacement versus time curve that I had in the previous slide. I've just had to squish it down so I could fit a couple of blank graphs on here. One of those graphs is going to be my velocity versus time graph right here, and the other one is going to be acceleration versus time. So like I said in the previous slide, what I want to do is I want to find the slope of the tangent line at different points along this curve. So let's take a tangent line. Well, actually, let me create some labels here first, x, v. And now let's take the slope of a tangent line right here. So this tangent line is horizontal, its slope is 0. So for my velocity right at that time, I'm going to put 0. So I'm going to plot a point right there. When I get to this point right here where my displacement is equal to 0 for the first time, the slope of my graph is going to be a negative number, and it's going to be the most negative number that it's going to get, because after this my slope is going to get less and less negative, and before my slope was less and less negative than it is now. So this is the minimum slope that I will run into on my displacement versus time graph. So let's plot a point to represent that on this graph right here. So let's put a point right there. That's going to be our lowest point. Let's ignore the scale for now. Let's just worry more about the shape of what this thing is going to look like in the end. So I can continue to put more tangent lines down at certain points and calculate their slope. So right here I come back to 0, and then I can do this for the rest of the points on the curve, and I get a pattern that looks like this. Well, that kind of looks like it's going to be sinusoidal as well. It's some sort of sine or cosine. So let's connect those dots, and it turns out that the velocity looks like it is taking on the shape of a sine curve, but that sine curve is actually upside down. So it's actually negative sine. Well, what if I want to figure out acceleration? Now, just to be complete, since I've already talked about displacement and velocity, I might as well talk about acceleration, even though acceleration really doesn't factor into our kinetic or potential energy. But I can repeat the same process I did when going from displacement to velocity, because acceleration is the slope of a velocity versus time graph. So let's make this a plot of acceleration versus time, and what I notice is if I were to plot the slope of the tangent line at each of these points, I will get a curve that looks like this. And then after that it's going to come back up again, and it turns out that that curve looks something like this. And as a matter of fact, that looks like a negative cosine curve. Well, that's pretty interesting. So if my displacement takes the shape of a cosine curve, my velocity is going to take the shape of a negative sine curve, and my acceleration is going to take the shape of a negative cosine curve. Interesting. But what if my displacement isn't cosine? What if it is a sine, or what if it's negative sine? What if it's some other sine or cosine? Well, what I want you to do is I want you to write down these two tables very quickly. Write down sine, cosine, negative cosine. These things here aren't exactly important now, but I definitely want you to write down sine, cosine, negative cosine. And then displacement, I want you to write A. Velocity, I want you to write A times omega. And acceleration, I want you to write A times omega squared. So those of you in advanced physics, I'm going to actually teach you how to figure out what velocity and acceleration are if you have a certain trig function for your displacement. Those of you in AP, we have a much better way of doing this because we know calculus. I'm going to show that to you on the next slide, although you probably already know what that is. But you can stick along here and see what interesting relationship comes up here. And then you can confirm that on the next slide with some calculus. But anyway, advanced physics, let's go ahead and do this. So let's say that this is my displacement curve. It's a cosine curve. Okay. So if I find out my displacement is a cosine curve, for example, x of t is equal to a times cosine of something inside here that depends on time. And if I want to figure out what its velocity curve is, well, it turns out that when I go from x to velocity, I jump down in this table. So I'm going to go from cosine to negative sine. So I'm going to get v of t equals a times omega. Now remember, because I'm dealing with velocity, instead of a, I want to put a omega out in front instead of just a. So instead of a, I want a omega. And then instead of cosine, I now want negative sine. But I don't want to put the negative after. I want to put the negative before everything. So let's put the negative sign there. And then let's finish that off with sine of omega t plus phi. So velocity as a function of time is equal to negative a times omega times sine of omega t plus phi. If I want to write out acceleration for this, I'm going to jump down another spot in the table, and I'm going to go, instead of using velocity, I'm now going to use this as my coefficient for acceleration. So my new coefficient is a omega squared. And then I jump down to negative cosine of omega t plus phi. So I will end up with this as the expression for my acceleration as a function of time. Now let me give you another example, just in case, let's say that instead of a displacement being a cosine curve, let's say that displacement is equal to -2 times sine of 3 pi t. So how would you handle that with these two tables? Well, I notice that it is a negative sign. So actually my displacement starts here in the table. So that's where my displacement is. If I want to jump down to velocity, I better go from here down one. So my velocity is going to have the shape of a negative cosine. Out in front is going to have a omega instead of a. So instead of -2, I am going to have -2 times omega. Well, omega is the coefficient in front of t, so I am going to have -2 times 3 pi. So let's write that out. V equals -2 times 3 pi times cosine of omega, or 3 pi t. Right? What if I want to go one step further and write acceleration? Well, what happens after you reach the bottom of this table is that now we have to wrap around and go all the way up to the top. So if I'm going from velocity to acceleration and I'm already at the bottom of my little table, I have to go all the way back up to the top again. So let's go all the way back up to the top. And now I want to add on another power of omega. So instead of 3 pi, I am going to have 3 pi, all of that squared. So my coefficient is going to be 2 times 3 pi squared. And remember that now my sign is positive, which is why I lost the negative sign right there. Because now I'm dealing with a positive sign graph, not a negative sign graph. Okay, so that's how you can quickly switch between displacement, velocity, and acceleration when you're dealing with simple harmonic motion. This next slide is going to be some notes for AP only. So those of you who are in advanced physics, I want you to scrub on your controller for the video player until you get to the next slide, and then you can join us back up there. All right, so AP Physics. Rather than memorizing a chart, I mean, we can use calculus, right? So we can take the derivative of x with respect to time to get velocity. And in order to do that, we have to differentiate this thing right here. And when we do that, we get, well, actually, I'm going to do it by substitution. So let's substitute W for this omega t plus phi inside of here. And then I'm going to apply the chain rule, so I have to take d of dw, excuse me, let me back that up. I have to differentiate this with respect to w, and then I have to multiply that times dw dt, because that's the chain rule. So when I take the derivative of this with respect to w, I get a times negative sine of w, and then dw dt, when you look over here, that is equal to omega. So my velocity is going to equal negative a times omega times sine of w. But now let me plug in this back in for w. So I get negative a omega sine of omega t plus phi. And that is the same thing that we came up with in our little handy-dandy trick table on the previous slide. If I want to go from velocity to acceleration, well, acceleration is equal to dv dt, and you can differentiate this with respect to time one more time, very similarly to the way I did it up here. And you're going to end up with negative a times omega squared times cosine of omega t plus phi. So that's how I came up with that handy-dandy little chart on the previous slide. I just remembered what my differentiation rules were, and you'll notice that if I started off with, let's say, I started off with negative sine as displacement, then I would go to negative cosine, And then what is the derivative of negative cosine? Well, that turns out to be positive sine. So that's why that little table on the right-hand side of the previous slide works so well, is because these all end up being derivatives of one another in one shape or form. All right, so now let's talk about kinetic energy of an object in simple harmonic motion. So we know that kinetic energy is equal to 1/2 mv squared. So if I have a displacement curve where x is equal to a times cosine of omega t plus phi, I can use my handy dandy chart to find out that v is equal to negative a omega times sine of omega t plus phi. If I take the square of that, because after all I want v squared, right? If I take the square of that, it's going to equal a squared omega squared times sine squared of omega t plus phi. So let's replace v squared with this whole thing over here. And for kinetic energy, we end up with 1/2 m a squared omega squared sine squared of omega t plus phi. Now that looks pretty confusing and not very interesting, but we can recognize a couple of things in here. First of all, I know that a times omega is going to be the maximum speed that our mass is going to have on the end of the spring. After all, if v is equal to this times negative sine of omega t plus phi, well, this has to be the maximum value that it can take on, right? Because its maximum value is 1. So I know that a times omega is equal to v max. So if I were to use that and replace this with, actually not v max, but v max squared, now I get that kinetic energy is 1/2 m v max squared times sine squared of omega t plus phi. Well, this looks like the maximum kinetic energy that the object can have. So the kinetic energy at any given time is equal to its maximum kinetic energy times sine squared of omega t plus phi. So those are a few different ways that you can actually express kinetic energy of an object in simple harmonic motion. Well, let's figure out what the potential energy of an object in simple harmonic motion is. Well, that is equal to 1/2 times kx squared. That is the potential energy of something at the end of a spring that's undergoing a spring force. Well, we know that x is equal to a times cosine of omega t plus phi. At least it is for our example here. So if I square that, I get a squared times cosine squared of omega t plus phi. So now I can write that the potential energy is equal to 1/2 k times a squared cosine squared omega t plus phi. Well, again, that doesn't look very interesting. So we can write that the maximum displacement x is going to be our amplitude a. So I can write that the potential energy is 1/2 k x max squared times cosine squared of omega t plus phi. And then if I recognize that this is the maximum potential energy the object can have, well, now I just write PE equals PE max times cosine squared of omega t plus phi. So I could use any of these three to use as an equation for the potential energy of an object in simple harmonic motion. Now this next slide, I decided to switch this to AP only because this involves a lot of manipulation of symbols. Now that doesn't mean that you in advance can't handle it, but I usually don't deal with that with my advanced class, so you're not obligated to watch this. Just make sure you go on to the next slide, the final slide, and get the final notes from there. You'll see all of this summarized on the next slide anyway, but I want to actually get the nitty-gritty math details for AP and other people who want to stick along. So welcome if you're going to stick along. So I just came up with kinetic energy. I just came up with potential energy. Now let's add those two together to get the total energy of our system. So we had E tot equals 1/2. We had this big thing for kinetic energy, and we ended up with this big thing for potential energy. And it looks awful confusing and very vague just by looking at this. But there are some things that we can glean from this. First of all, omega squared, we know, is equal to K over M. So I can replace omega squared with K over M, and I get something that looks like this. So all I did is I took omega squared, replaced it with K over M. Well, let's do a little bit of simplifying in this term now. The m's divide out. So now I have, and if I rearrange this K in front of the a squared, now I have 1/2 K a squared times sine squared omega t plus phi plus 1/2 K a squared times cosine squared omega t plus phi. Well, those two things have a common factor, don't they? It's 1/2 K a squared. They share a common factor, so let's factor that out. So I have total energy equals the 1/2 K a squared, and now I have sine squared omega t plus phi plus cosine squared omega t plus phi in parentheses. Now we have to recall a trig identity, a very important one. That is that sine squared of x plus cosine squared of x is equal to 1. Now if that's true, then this entire thing in parentheses is equal to 1, or this entire thing in brackets is equal to 1. So my total energy, E total, is equal to 1/2 K times a squared, or you can say it's equal to 1/2 times K times its maximum displacement squared. Okay, let's actually plot the total energy, which is equal to kinetic plus potential for our object in simple harmonic motion. So again, this top graph is its displacement versus time. And now let's plot its potential energy as a function of time, which is equal to 1/2 times K times x squared. So I'm going to plot this squared. It's going to have this shape right here. So it's going to have the shape of cosine squared of x. And then let's plot the kinetic energy. The kinetic energy is equal to 1/2 mv squared. And if you were to plot that, like I did here in blue, it would turn out to look like, oh, sorry, I forgot something there, so let me back this up. All right, I don't want to show that just yet. This blue curve is going to be sine squared of, actually I shouldn't write x. I should write it out. It's 4 pi t. Because that's what I have up here. Actually, I need to change that to a t as well. Oh my goodness, I forgot to change some things there. It's x as a function of time, so this should be 4 pi t, not 4 pi x. Sorry about that. And then this thing down here at the bottom right, this should be sine squared of 4 pi t. And this should be cosine squared of 4 pi t. Oops. Okay. Well, it turns out when you add these two things together, it turns out that you get a constant E total, and that E total, boy, again, I wrote it in a bad spot, didn't I? So let me back that up and rewrite it. So this E total, when I add kinetic plus potential, this E total is equal to 1/2 times K times the amplitude squared. Okay. Or you can say it's equal to 1/2 times K times the maximum displacement of our mass away from its equilibrium point. And that is constant with respect to time. That doesn't change. It doesn't go up or down. So what does that tell us about our system? It tells us, well, I still didn't get rid of that, did I? Yeah. Why does it keep on doing that? I'm not sure, but we're going to get rid of that. All right. So it tells us that the total energy is indeed conserved in an object that's in simple harmonic motion. And its total energy is given by this formula right here. Okay, well, that's it for energy of an object in simple harmonic motion. And I look forward to seeing you in class pretty soon, where we can solve some problems involving kinetic energy, potential energy, total energy of an object in simple harmonic motion. All right, have a good afternoon. Bye.